Alrighty, so this is going on 143 when we're done. So we're going to look at polar coordinates, what we have been plotting things in, and the only coordinate system that you have ever plotted anything in, most likely, is the rectangular coordinate system or the Cartesian coordinate plane. This is the same thing. It's just your normal XY axis that you are used to seeing. But there are different types of coordinate systems, and coordinate systems are really nothing more than a way to define a point in space. Okay, it's just telling us where it is in space and gives us something to reference. Okay, so in the Cartesian coordinate system, or the rectangular coordinate system that you are used to using, we use the coordinates x, y to define a point, right? So we start at the origin, and then the x moves which way? Left or right, so that would be what? This was one word. Horizontally, good. So then moving x units horizontally, and followed by y units vertically, right? Makes sense, yes? It's what we've been doing. Nothing new there, no surprises. And could you go vertically first, as long as you did y? Could you go vertically first and then horizontally and get to the same point? Yeah, you could. Doesn't matter. Just make sure you know which is which, that sort of thing. So once you do that, that gives you this point here, which is xy. Okay. So we're going to look at that same point. I repeated it right here. And let's think about, instead of going horizontally and then vertically, what if I just went from the origin directly to this point? Tell me something about that pink dotted line I just put on there. Anything? It's diagonal. Okay. Could I find the length of it? Yes. Does this look similar to what we did before spring break? Do y'all remember anything we did before spring break? We were doing vectors, right? Okay. So, oh yeah. All right, so this is y, this is x, and this is y, because we really just get like a little rectangle right there, right? So this diagonal, how can I find that? Pythagorean theorem, right? X squared plus y squared equals, and what letter were we using here? R, right? We were using R for the resultant, right? So let's think about that. If we have this right triangle right here, I could find R. R is the square root of x squared plus y squared, right? That gives me the distance the point is from the origin. Make sense? Now, we haven't been allowed to count diagonally on the rectangular coordinate system because that doesn't work that way, right? You can't go diagonally through and count that way. We can only go horizontally and vertically. But we're going to change to the polar coordinate system, which means our graph looks different. So we actually can go diagonally to find distance. And then instead of worrying about horizontally and vertically, I just want the distance from the origin and how much I rotate. So this right here would be my theta. Okay. So that's basically, this is kind of ends up being the same. Today we're not actually going to find the points. I'm going to give you the points and we're just plotting. But when we get to translating between the two coordinate systems, it's really the exact same thing we were doing with vectors, right? You have the x and the y and you relate it to r and theta, just like r cosine theta, r sine theta. It's really the exact same thing, okay? So instead of I go right and then up, I would figure out a distance and how much I have to rotate to get to that same point. So our ordered pairs are going to look like this, r comma theta. So in the polar coordinate system, instead of moving vertically and horizontally from the origin, we use the distance from the origin. So that's going to be r, and the rotation angle, which is going to be theta, in standard position. Okay. Two different ways. These are two different ways that I could get to the exact same point. It's still defining the same point in the exact same place in space, just using two different coordinate systems. Okay, and there's reasons that we need the different coordinate systems. We're really just going to look at the whole graphing of it right now. So here's one example of what a polar graph or a polar grid would look like. And I say one example because we could have more lines in there, just like with the rectangular coordinate system. You could have them closer together, the boxes closer together, or depending how, what your scale is. So it says the polar graph is a series of concentric circles. Remember what concentric circles are? What does that mean? They have the what? I thought somebody said something. What'd you say? Circles with the same what? What is centric make it sound like we're talking about? The center. What does con mean? What does con queso mean? With cheese, right? Okay, that's the only Spanish I know besides the bad words. With cheese, con queso. Isn't that what it means? Okay, so concentric means with the same center. Make sense? Okay, so concentric circles. It's like if you drop a pebble in water and the circles go out, those are concentric circles. All right, so serious, because if you don't know what it means, then me writing concentric there doesn't mean anything. Concentric, with the same center, right? So concentric circles around a central point. So instead of this being the origin in this coordinate system, it is called the pole. So the plane appears this way because the polar coordinates are given to you as a radius, which is really the distance, and an angle, which gives us direction. So it's distance and direction, just like a vector is. Except this time it's really just a point and we're not drawing a little arrow. It's not the vector itself, not the little segment, directed segment. It's a directed point, okay? So each circle represents one radius unit. So on the x-axis, you would count out the same way you would if it was a rectangular coordinate system, right? This is 1, 2, 3, 4. But then you get to count diagonally, which you didn't get to do in the rectangular coordinate system. And then this is 1, 2, 3, 4, because it's just a radius unit. Okay. And each line represents the special angles from the unit circle. Okay. Everybody good with that? Now, this particular graph that I gave you has just the special angles that you had to know, but most of the grids that you're going to have and the ones that are on the homework and the ones that I'm going to put on the future notes will also have another one coming in through here, which means we're really counting by pi 12ths as we go around. So they'll be partly labeled. You'll be able to figure out which ones you're using. And sometimes it's in radians, sometimes it's in degrees, so we need to understand both. Right? So we're going to write all points on the polar plane as r comma theta. So when you do that, even though, and this is why I asked you about the x, y, we always go left and right and then up and down. Like we go in the order that we see it. You can do that here. However, it is easier and better in the long run with the different things that are going to pop up if you do the theta first and then the radius. It does work both ways, but when the radius is negative, it can get kind of confusing as to what to do. So it's better to find the angle and then find the radius. Right? So we're going to find theta first, then locate the radius on that line. And these are lines, even though they look like line segments, because the circles can keep going. Obviously, I could have a radius bigger than 4, so the circles could go out for infinity, which means that these would go out as well. All right. We all good? All right, so let's plot some points. We're going to start with, oh goodness, okay, so mine's so big we can't even see it. So the first one that you have is point A. It's 2 and then pi fourths. So we're going to go to, we start at 0 because it's standard position, go to pi fourths. Right, so here's the line that represents pi fourths, and my radius is 2, so my point is right here. There's point A. Easy enough? Okay, it's really not that bad. All right, so now let's look at this -3 pi sixths. Okay, so here's where it can get really confusing if you try and do the radius first. It still might be a little confusing at first when we do the angle first. But we go to pi sixths, right? So here's the line that is pi sixths. If it was +3, then my point would be right here. But it's a -3. So once you find your angle, If it's negative, you go through the pole and go 3 on the other side of it. And there's that point. Does that make sense to you? Okay, so you still find the angle, but then the negative means you go through the pole to find your distance. Then we'll do C together, and then I'll let you do the other 3. So on C, it's 2 and then negative 2 pi thirds. So negative 2 pi thirds means I'm starting here, but I'm going clockwise, right? And so 2 pi thirds, if I went positive, would be this much. So if when I go negative, it's going to be here, right? So here's my negative 2 pi thirds. And what was it? 2? Positive 2. And there it is. C. We all okay with that? All right, so I'm going to give you a second. I want you to plot the next 3 points on your own, and then while I check roll, and then we'll talk about them. All right, Zeke's going to plot D for us while y'all finish the other ones. Not as easy as it looks, is it? I know. Even when I calibrate it, it's all off. Okay? Good job. All right, y'all agree with D? Yeah? Who wants to do E? Pick you. I choose you. All right. You can do it. All right, Nathan's going to do E for us. All right, y'all agree with E? Yes, because on this one, you had to go negative 5 pi fourths, which ends up here, and then it's a negative 1, so you come through the pole, and there's E. All right. Katie, you want to do F? You know you want to. That was a yes. I heard it. All right. Y'all agree with that? We good? All right. Any questions about any of them? Easy enough to plot? Today, all we're doing is plotting. That's it. Okay? And while plotting and then coming up with points that are plotted at some point, but we're not having to convert or find equations or do anything else at this point. Are we all good? All right. So let's look at the next one. I'm going to give you a minute, and I want you to plot these 2 points that I gave you here. Okay, plot points A and B on this graph right here. Okay, so what do you notice about them? They're the same point, right? Because there's point A, and then B is at 5 pi fourths negative 2. So when I rotate around to 5 pi fourths, I'm here. But when I go through the pole to the negative 2, A and B are the same point. Does that happen in the rectangular coordinate system? Can you plot 2 points that look completely different and they end up in the exact same spot? No. If I tell you to go on the rectangular coordinate system and plot the point 2, 3, you go 1, 2, 1, 2, 3. Like, there's your point. There's no other coordinates that I could give you where you'd end up in that exact same spot, right? It doesn't work that way. But in the polar coordinate system, it does work that way. How many different points do you think I could give you and you still land right there? A bunch. What's our fancy math word for a bunch? An infinite, good. Yeah, and because I could keep adding, like this is pi fourths, right? I could add 2 pi and still be at 2. I could add 2 pi, 2 pi, or I could subtract 2 pi, or I could go to 5 pi fourths and add or subtract 2 pi all the way around and then make it a negative 2 and end up in the exact same one, all right? So what we normally do on here is find 4 and just have our range be from 0 to 2 pi. Right, so I want you to think about the fact that these are the same point, right? I want you to find the other two that are between 0 and 2 pi. Or, I'm sorry, negative 2 pi to 2 pi is what I should say. So I'm here at pi fourths. I could add 2 pi, but then that gets me above 2 pi, right? So instead, what I would need to do is get here going negative. So this would be a negative what? 7 pi fourths, right? Because it has this reflection right here. So if this right here is pi fourths, then here's pi fourths right here. So this would be negative 7 pi fourths. And if I go negative 7 pi fourths, what's the radius? Positive or negative? Positive, okay? So one of them would be a positive 2, negative 7 pi fourths. Right. And so if I can only go between negative 2 pi and 2 pi, then I've got a positive and negative radius here. This is a positive one. This means I need a negative radius. So I really need to end up here. So I can go a negative 2. So instead of a positive 5 pi fourths, this would be a negative what? 3 pi fourths. Good. So this would be negative 2, negative 3 pi fourths. And then notice what happens here when you do that is that you got pi fourths and then negative 3 pi fourths. And 5 pi fourths and negative 7 pi fourths. If you ignore the signs on the angles, then you have one in each quadrant. Does that make sense to you? So you can make sure you just got to figure out which one's positive and negative. Because if you repeat something, something isn't right somewhere. So that's the other two. But truly, there are an infinite amount of answers, right? So there's really, even though, an infinite number of answers. So let's just talk about what that would look like, okay? If I have a positive 2, and that was at pi fourths, right? Then that would be plus or minus 2 pi times n, right? Just some multiples of 2 pi. Or negative 2 and 5 pi fourths plus or minus 2 pi n. Right now, we're not talking about ginormous ones or anything. I just want you to understand that there are an infinite amount, but when you're asked for 4, you're asked for the 4 that go from negative 2 pi to 2 pi. Okay? Easy enough? You can handle that? Yes? Do you have to know your special angles? Yes. That's why I keep saying you got to know your unit circle. All right, so I'm going to give you your assignments, and it is 2 pieces of paper stapled together, so I hope you can handle this ginormous packet. But one of the reasons it is like that is so that you had a different grid on each one so you wouldn't confuse yourself. So the grass is what makes it so big.